Here I have 3 more problems in real analysis. The first problem says that we have an integrable function f on the unit interval 0 to 1, L1 integrable. We want to prove that there exists a number c in between 0 and 1 such that the integral from 0 to c of fx is equal to the integral from c to 1 of fx. So essentially what you're saying is that you can cut the area under the curve in half. Okay, or well, half in terms of area. So we need to figure out if this c exists. Okay, so the way we do it is that we're going to define a function, big F of c is what we'll call it, that's equal to the integral from 0 to c of f dm subtract integral 0 to 1, or excuse me, not 0 to 1, c to 1. C to 1 f dm. So what I've done here is I've essentially subtracted this off from this side to this side and defined a function fc. And the idea of this proof is that we're going to want to show that at some point this function crosses the x-axis. Alright, so notice that since the antiderivative from 0 to c, like if this was a function in and of itself, it would be a continuous function. So notice that f of c itself is a function, or a continuous function. F of c is continuous. And if we plug in 0 into the function, f of 0, what would we get? Well, f of 0 means that this c is 0, so this whole thing will die and will just be 0. And you'll get negative integral from 0 to 1 f dm. So it's the opposite of the entire integral. But if you plug in 1 into this guy, then you'll get 0 to 1 integral here, and then this guy will die, but this guy would just be the negative of that guy. So it's not too hard to show just by using algebra that we have this relation, or this equation. So f of 0 is equal to negative f of 1. And now we have 2 cases. If f of 0 does not equal 0, meaning that negative f1 is not equal to 0, then we can apply the intermediate value theorem, which says that there exists a c naught such that f of c naught is equal to 0. If the function is negative at some point and positive at another, and the function is continuous, then you know it has to cross the x-axis, so it has a root, if you want to call it that way. Or a 0, I guess is the more appropriate word. I like to say roots. I know it's probably not proper to use the word root, but I don't know. It's just, I default to root. I should probably say zeros more because I think that's what the literature says. Now, if f of 0 is equal to 0, then we can just choose c to be 0 or 1. Because remember, it's c between 0 and 1 and including the endpoints. So you can just set c equal to that number and everything will be fine. Alright, so that's the first problem. This was not a homework problem or a qualifier problem. I just found this one on the internet that came with its own solution. I think I got it off a website that had exercises in real analysis. So I chose this one because it wasn't too hard. It's only like 3 lines, I think. I mean, technically 4 lines, I guess, if you want to be pedantic about it, but I think you can get it down to 3. Alright, so the second problem is an old qualifier problem. I believe it's from 2015. We have a sequence of Lebesgue measurable functions on the unit interval to r. We are told that the output of fn, is between 0 and 3/2 for any input, and for any n. So this is the range of fn for all n. And we're told that the integral over the domain is equal to 1. And I did not write my equal sign for some reason. And what is it that we want to prove? We want to prove that the Lebesgue measure of this set is bounded below by 1/2. Okay. So what are we going to do? Well, I'm going to give this set a name to make my life a little bit easier. So we'll let A be equal to X such that lim sup Fnx bigger than equal to 1/2. And rather than call it A complement, I'm going to call it B. You can call it A complement if you want, but we're going to call this set B. Okay, so now what am I going to do? Well, we've been given two things to play with. So let's start with this guy. We're going to write down the integral from 0 to 1 Fn dm, which is equal to 1, but I don't have to write that right now. What I want to do is basically split this up over these two sets. So we have integral over A Fn dm plus integral B Fn dm, and we're going to denote these two integrals as IA and IB. And I should explicitly state which one's IA and IB, but I think it's kind of clear from the context which one is which. Again, these problems aren't supposed to be in a paper for other people to read. They're really just for note taking. All right. So what can we say about IA? We're interested in bounding him from above. So we know that IA is less than or equal to the integral over A dm. And I need to place something inside here that will bound IA above. And essentially, we need to bound the function above by something. But we have been told that. Up here, Fn is less than or equal to 3/2, so I can plug in 3/2. But this just becomes 3/2 integral A dm. But this integral becomes the measure of A. So I have 3/2. Man, my handwriting has gotten worse. Measure of A. All right. So how are we going to play with this to get the measure of A bigger than equal to 1/2? Because that's essentially what this statement is, right? Once I plug A in for this. Well, I know that 1 is equal to lim sup integral 0 to 1 Fn dm as n tends toward infinity. And that is less than, because I know what this limit is equal to, right? Because this integral is always equal to 1, so I can take the lim sup of it without, pause for thought. But this should be less than or equal to 3/2 measure of A plus 1/2 measure of B. Now I have to pause here for a second and ask myself, why am I writing 1/2 measure B? Well, if we were to write out the integral of IB, we would get the integral over A complement, which is B. So we have measure of B there. But over B, heck, I should write it out. I don't know why I'm skipping details. IB is equal to the integral over B of Fn dm. But in B, we're bounded above by 1/2, right? Yeah, 1/2. So this should be less than or equal to 1/2 integral over B dm, which is 1/2 measure B. So I get this guy. Also in my notes that I'm looking at here, apparently Fatou's lemma shows up in here somewhere. I thought this was good enough to justify this step, but in case I'm wrong and there's something in my notes that I don't understand, I'm going to write Fatou's lemma. Because I do know that Fatou says that integral of f is less than or equal to lim inf of integral fn. And you can rewrite that with lim sup, which I believe is what this lim sup is over here. Okay, so I guess that does kind of make sense now that I think about it. All right, so now what can we say? Well, remember, we are on the unit interval, and I've split the unit interval into two pieces here, A and B. So if I want to rewrite this line here with just measure A, I can write 3/2 measure A plus 1/2, and then in parentheses I have 1 subtract measure A, because the measure of A plus the measure of B has to be equal to 1. And now combining this, I get 3/2 measure A plus 1/2 subtract 1/2 measure A, and that becomes measure A plus 1/2. And so what do I have now? I have 1 is less than or equal to measure of A plus 1/2. So if I subtract 1/2 from both sides, I'll get 1/2 less than or equal to measure A. And that is exactly what we wanted to show, this statement here. So overall, a pretty decent problem. I remember when I first entered the program, I tried this problem. Someone had showed it to me, and I monkeyed with it for a little bit, but I was not prepared enough to solve it at the time. Although I think now I could probably do it without much effort. Just goes to show you, if you practice every day, you'll get better. And we have the third problem I decided to show you. And in full disclosure, I do not like this problem. I do not like it because I don't understand it. And I've tried understanding it for a while, just trying to justify every step. This was not a homework problem nor a qual problem. I'm not entirely sure where it came from. I just know who wrote it and who gave the answer. And then a friend of mine gave it to me because he knew I was interested in collecting analysis problems. And he said, here's a problem from so-and-so, and he solved it, his own problem. And I thought you would like to have it. And I said, yes, please, I would really like to have it. So this is his problem and his solution. And I'm going to try and explain it as best as I can. But there's a step at the very end that I'm kind of shaky on. So what does the problem say? We want to find alpha, beta, and gamma positives such that the triple integral converges. And you can see what the triple integral says. And the domain that we're integrating over. So how does this proof start? Well, we notice that x, y, and z are bigger than 1 from this part up here, which tells me that x to the alpha plus y to the beta plus z to the gamma has to be less than or equal to 1 over t for some t. T positive. I mean, it's kind of redundant, but I'll write it down. Now, the idea here is that we want to estimate the size of the three-dimensional Lebesgue measure of the following set. X, Y, Z, such that X alpha plus Y beta plus Z gamma is less than 1 over T. So this is our goal. Well, one thing is obvious to me. If T is bigger than or equal to 1, then the three-dimensional Lebesgue measure of this set, to save pencil space, I'm just going to write ... but just know that I'm talking about that set. That measure is 0. Why? Well, it comes from the fact that x plus y plus z is bigger than or equal to 3, because we have x, y, and z all bounded below by 1. So the smallest this could ever be is 3. And if t is bigger than 1, then this says that this is less than equal to 1. And that is nonsense. In which case that set is empty and the measure of the empty set is always 0. Okay, now comes the first part where I'm kind of not really confident with. So we need to find the integral from 0 to 1 of the 3-dimensional Lebesgue measure of this guy, dt converges. I'm a bit sketchy about putting this in here. I know technically it's a function because it's a 3-dimensional Lebesgue measure, but I still don't like the way it's written. But I know what it's trying to say. If x to the alpha plus y to the beta plus z to the gamma is less than or equal to 1 over t, then I can say that from a very crude estimate that x to the alpha is less than or equal to t to the negative 1 over alpha. And then the same idea, oh, sorry, no alpha here. I took the alpha root. And then the same thing for the y's, except I replace them with beta and gamma for the z. So we have those crude bounds. Furthermore, if x to the alpha, y to the beta, and z to the gamma are all less than or equal to 1 over 3t, so essentially I'm making it less than 1/3 of 1 over t, right? Because if I add them all together, I'll get this guy up here. So I'll be happy there and I can get my estimate. Then I know that x to the alpha plus y to the beta plus z to the gamma is less than or equal to 1 over t. I don't know how appropriate it is to write it this way with the commas. So maybe explicitly write out each individual inequality, because there's 3 of them here. I don't know if that's clear, but for me, I'm able to understand it written this way. I think I wrote this on the chalkboard once when I was doing a homework problem, something similar to this. And I knew what I meant, but the instructor kind of grumbled at me that what I had written wasn't proper, I think. And so just make sure that other people in the room know exactly what you mean when you write at the board. But for me, I understand what I'm talking about. So when I'm taking notes, I don't waste time writing out every explicit detail. But if other people are reading it, you should do that. Always be a stickler for details. Okay, so now if I take each individual inequality and take the alpha, beta, or gamma root, respectively, then I know that the following holds. 1 less than or equal to x less than or equal to 1 over 3 t to the 1 over alpha. And I'll write similarly for y and z. Okay. Now here comes the fun part, because this is the part where I don't really understand the proof too well, and hopefully someone can explain it to me. So 1 over 3t raised to the 1 over alpha, 1 over 3t 1 over beta, and 1 over 3t to the 1 over gamma is greater than or equal to 1/8 times 1 over 3 raised to the inverse alpha plus inverse beta plus inverse gamma times t raised to the negative alpha inverse plus beta inverse plus gamma inverse. And what I mean here is that each of these 3 things separately, considered separately, so cover that part up and say, okay, that bit there is greater than or equal to this over here. And the same idea for these 2. Again, your instructor might grumble if you write it this way on a test or something, but here I know what I mean. I'm saying that each of these individual 3 things are bounded below by that guy. So when I look at this statement here, just before I finish, I want to say a few things. I can appreciate the part to the right of my fingers, so because you can multiply those three together and then you just end up adding the exponents together, and the same thing for the t. But the 1/8 always makes me nervous. I don't know where the 8 comes from. It's the one part of this proof I don't truly understand. I felt like someone told me at one point, like a year ago when I was studying, but I've lost track of it. I don't know where it came from or where it went. And I feel like it's obvious. That's the thing that's kind of killing me right now. But I'm sure I'll see it as soon as I upload this video. That's usually how it goes. All right, so let's finish this guy because I'm getting tired of him. Integral 0 to 1 t raised to the negative alpha inverse plus beta inverse. Plus gamma inverse. dt finite. This happens when this guy is integrable, obviously, on this domain. So using our basic calculus knowledge, we know that the exponent here, I'll drop off the negative and just correct it with the inequality down here. We know that this guy has to be less than 1, and these are positive. So that sum has to be between 0 and 1. And that's the proof, more or less. I feel like the 1/8 is somehow related to 2 cubed. But maybe I overlooked something in the proof. Like maybe I'm missing a line. But I copied it down exactly from what was written. But I guess it's possible. I mean, because that makes sense, right? If you're going to multiply all three of them together, you're going to get 1/2 times 1/2 times 1/2 if you just take half of it, right? Man. Because, all right, it's not coming to me. I thought I was onto something here, but I think that's good enough. All right, if you see where this 1/8 comes from, I'm pretty sure it comes from 1/2 cubed because I have 3 of these things here, and I'm taking half of it somewhere. I think that's in the proof somewhere. I wish I understood it better, but this video is really just to help me go back over it and maybe show you just kind of the stuff I'm working on, and as well as help me down the road. Anyway, I'm rambling too much. Thank you for watching.